Good morning, everyone. So welcome back to the workshop on quantitative methods for population dynamics. I'm going to share my screen. I hope you had a nice day yesterday. Let me share my screen. So again, this is the website we've been using for the workshop. Okay, you have everything you need, the packages you need to install, the links to the YouTube sessions, and also the schedule here. So yesterday, Aurélien covered the estimation of abundance and density of populations, going through conventional methods and the detectability issues. And then he covered several methods to estimate abundance, including capture-recapture closed population models, distance sampling, and admixture models. And then I followed Aurélien with the estimation of demographic parameters using capture-recapture models. And we covered the estimation of survival from capture-recapture data. And also we covered the incorporation of covariates to explain variation, either individual variation or temporal variation, so variation across time. And today, so we're going to resume this lecture on survival estimation. And I will start by telling you a few things about the assumptions on which capture-recapture models rely on. So there are a few assumptions that we need to double check before we can safely apply these models. First, there are a few assumptions related to the design. So we shouldn't have any mark lost. Also, we need to identify the individuals without error. Otherwise, we generate false positives, and you can imagine how it might screw up our analysis. And also, we need to capture individuals as a random sample. Otherwise, if we only capture, I don't know, only all the individuals and we try to assess the effect of age on survival, this won't work. There are some assumptions related to the model itself. So we should have a homogeneity in survival and recapture probabilities. And we will see in a minute how to relax this assumption. And also, we need to have independence between individuals. Otherwise, we get some over dispersion. And although it's possible to account for that, the general advice is to try and do our best to have a sample of independent individuals. And to test the validity of these assumptions, there are some tests like Aurélien told you about for closed populations. And these tests are summarized in this nice paper by Roger Pradel and colleagues. And these tests have been implemented in R, in the package R2UK, for which we provide a paper and a vignette here. So feel free to have a look to that. I won't cover that today because it's kind of not a workshop in itself, but at least half a day about goodness of tests, and we won't have time to cover these topics. But feel free to have a look to the paper and the vignette. So you just have to click on the link here. Also, before we proceed with multi-state capture-recapture models, I'd like to tell you a few words about what survival actually means in capture-recapture. The important thing to remember is that survival refers to the study area, and that mortality and permanent immigration are confounded. We cannot really distinguish the two. And so what we estimate is apparent survival, not true survival. What do I mean by apparent survival? This is the product of true survival and the fidelity of individuals to the study area. Okay, so this is always the product of the two. And there are some situations where if area fidelity, the fidelity to the study area is 1, then apparent survival is true survival, no problem. Okay, but in general, apparent survival will be lower than true survival. So the recommendation is to use caution when you interpret survival. And there are some ways to make sure that apparent survival is as close as possible as true survival by using, for example, ring recovery data. So you have data on dead individuals. So by definition, you know the date of death, and you get actual survival, true survival. So it kind of a correct apparent survival if you have some individuals for which you know the true date of death. And also there are some recent methods to include special information on survival that can get you a bit closer to true survival. Okay, the last part of this lecture on estimating demographic parameters is about estimating transitions between sites and states. And we will see in a minute what I mean by states, but sites you already have a rough idea of what I mean. Let's say we have two sites, wintering sites, colonies or whatever, ponds for amphibians, or so a site A and a site B. And you may move from site A to site B, or from site B to site A, or you may decide to remain on site A for one time interval or for several time intervals, or on site B if you're already on site B, okay? So it's exactly the same thing that we saw yesterday, but in addition to survival, we're gonna estimate transition probabilities between those two sites, okay, site A and site B. And transition from A to B, from B to A, and the transition from A to A or B to B, right? So let's go back to this representation using binary trees, the representation of the fate of individuals. So now we have two sites, A and B. So it may be first captured, marked, and released in A or in B. If you are first captured, marked, and released in A, then you have two options. Either to go to time 2, either you survive or you die or you emigrate. Okay. If you survive, there are two options, conditional on surviving. You may remain on site A with probability psi AA. So that's the transition from A to A. So that probability of staying on site A. Okay, so you're alive and present in site A, or conditional on your survival starting from A. Well, you may decide to move from A to B, okay, to do the dispersal from A to B, so with probability psi AB. And you end up alive and present inside B, okay? And of course, if you're alive and present inside A, you may be detected with probability PA for detection probability inside A, or undetected with probability 1 minus PA, which is the probability of non-detection inside A. Okay, and if you're alive and present inside B, you may get detected inside B with probability PB, or undetected with probability 1 minus PB. Okay, if you're alive and present in B, you cannot be detected or undetected with probability PA. It's for sure PB. Okay, same thing for alive and present inside A. So you see right away that with only two sites, everything gets a bit more involved than when you had one site with the Cormack-Joly-Sieber model, because we have many more combinations of alive in B or in A, detected or not in B or in A. I mean, things get much more involved, and we have many more combinations. And at the end, what we end up with is, if you detected on site A and first captured on site A, your encounter history is AA. If you're undetected in site A and first captured in site A, it's 8-0 for not detected, and then AB, A0, and 0. So you see that you have several combinations, several fates that lead to this encounter history A0. So first captured, marked, and released in site A, and then undetected. It might be that you died on the first time interval, or you were alive, but you moved to site B and you were not detected, or you were alive, but and you stayed in site A and you went undetected. So there are several paths that actually lead to the same capture history, A0. Now, what about if you're first captured and marked and released in site B? Well, by the same reasoning, you end up with this kind of encounter histories, BB, B0, B0, B0. So you see that with only 2 sites, we have many more combinations and only 2 sampling occasions. I haven't even covered the case with 3 sampling occasions. So multi-site capture-recapture models are much more involved than single-site Cormac-Joly-Sieber models, but they can, well, they're more involved, more complex, but it's expected because you can answer more questions about survival, but also about dispersal and the movement of individuals from one side to the other. Okay, so more questions, but more complex models. Okay, a little bit of history before we go for a live demonstration. These models were first proposed by Neil Arnason in the 70s. There are 2 papers or 3 papers in the early 70s, 72, 73. But then this, well, Neil, he proposed the equations, he had everything in the papers, but these models were not really used until the early 90s, where we had the computational abilities to actually feed these models because they are quite data hungry. And this is Carl Schwartz and again Neil Arnason and Jake Schwigert, who actually applied these models on salmons, I think. Let me check. Oh, Pacific herring in the west coast of Canada, and they tried to estimate survival and also movements between 2 or 3 sites. Okay, and quite rapidly, people realized that actually we can replace sites, wintering sites or colonies or ponds, like I said before, by states. By states, I mean, for example, Jim Nichols and colleagues came up with this nice idea of replacing a site, a physical site where you winter or you reproduce, by this one. It was by mass, by discrete classes of mass, of body mass. You see, and you can estimate transition between between classes of body mass. Or you can also replace site by breeding states, non-breeding, breeding with successful breeding or failed breeders. And you can, the same way you estimate dispersal between physical sites, you can also estimate the probability of moving from a state, a physiological state, a breeding state, to another breeding state. Okay, and it opens the way to, it opens a huge avenue towards addressing questions in evolutionary ecology and ecology in general. Okay, an example. Let's go through a few examples of multi-state models where you replace site by states. It could be, for example, epidemiological or disease states like sick or healthy. So you replace A and B by sick or healthy, or even uninfected, infected, and recovered. So there are many examples in the literature of using multi-site or multi-state capture-recapture models to kind of quantify the dynamic of diseases in the wild by estimating survival for sick and healthy individuals, but also the dynamic of the disease across time by estimating the transition between sick and healthy states, for example, or the other way around, between healthy and sick, so getting sick or recovering from a disease. And this is very interesting because you do that in wild conditions, so you account for the detection issues, for the detectability issues. This could be, the sites could be morphological states like we saw before, like classes of body mass, small, medium, big, so size, or light, medium, heavy body mass classes. The states could be breeding states, like I mentioned before, breeder and breeder, fight breeder, first time breeder, breeder with one or two offspring, and you see you can imagine how numerous the possibilities are to kind of use those capture-recapture models by just thinking of states in a large way, in a broad way. The states could be developmental or life history states, like juvenile, subadult, adult, which means that we could treat age as a state, because it's a categorical time-varying covariate where age is individual specific, but it varies across time. So you could use age as a state. And social states, like for social species, where you'd like to, for example, assess the impact of sociality on demography, and you could treat states as social states, like solitary and group living, or subordinate dominant, like in social species. So that's really the kind of questions you can address. And also, multi-state models are quite convenient to kind of combine different sources of information you have on individuals when you monitor them individually. For example, if you have information on alive individuals, like you have, well, you ring them and then you can recapture them, but you also have information on when they die, when it's exploited populations, for example. So you know when they die from harvest, and you know when they die from natural causes. So you can kind of disentangle the sources of mortality by using multi-state models. So in brief, state, it's an individual time-specific categorical covariate. So it's a covariate that is individual specific, it varies across time, and it's categorical in the sense that you have to discretize the covariate. So it can only be a finite number of classes. Okay? And you can account for that. You can deal with this kind of covariates with multi-state models, even though you cannot measure the state of an individual when it's undetected, of course. But the transition probabilities will account for that. So let's practice. To practice, we're going to use a kind of the equivalent of the deeper data set for multi-site models. It's a data set on Canada geese, which was published by Jay Hesbeck in the 90s in Ecology, if I remember correctly, where he and his colleagues studied wintering site fidelity of this species. And they had 3 sites, and they tried to assess the probability of transition of dispersal from one wintering site to the other. So the data we have, okay, so let me, yeah. So we have 1, 2, 3, 4, 5, 6 years. So 6 sampling occasions from 84 to 89, right? We have 3 sites, the Carolinas, Chesapeake, Mid-Atlantic, 3 wintering sites. And we have more than 21,000 banded geese, for which we know where they were in wintering for a given year. Okay, so now the coding is a bit different. We still have the zeros for non-detection. Okay, for example, this individual, a row is an individual. This individual was non-detected in year 1987, but in 86 he was detected. This individual was detected in site 2. So 2 is going to be Chesapeake, 1 is going to be Carolinas, and 3 is going to be Mid-Atlantic. Okay, so you see that, for example, this individual was first captured in Chesapeake, then we captured the year after in Chesapeake, then missed in 86. We didn't capture it in any of the 3 sites. And then in 87, it was recaptured in Chesapeake, and then it moved in the next year to the Mid-Atlantic wintering site, and then went back to the Chesapeake. Okay, so this is the kind of encounter history we have. We have detections, but on several sites. And this will give us some information on the transition between the sites. And we will account for the detectability issue here when we have non-detections. Let's go for a live demonstration. Okay, let me go back to the, that's this one. Okay, live demonstration on capture-recapture models. So once again, the data are in this zip file that you can find on the website. And we start by reading the data. Okay, so this file is called allgiz.csv, so it's a CSV file. And if you have a look to the data set, it's like I just showed in the lecture. You have the years, okay, the sampling occasion, and it's a bit different from what I saw. What I showed in the slide is that we have a last column here, which gathers all the individuals with that particular encounter history, meaning that, for example, this capture history with first captured. Oops, sorry, it starts here. First captured in the last year in 89 in the first site, you have 158 individuals with this kind of encounter history. 352 that were first captured in the second site, 271 in the third site, and so on. So we pull all individuals together with the same encounter history. It's just to summarize the data in a more compact way. Okay. In the slide, it was one individual per row. Here, it's one encounter history, one unique encounter history per row. Okay, and you have another column with the number of individuals with this particular encounter history. Okay, like in the deeper example, we need to work out the format. And we need to put these columns together in a single column of characters. So we're going to use again this function called unite. Okay, that put together all the columns from 84 to 89 together in a single column and with only characters. And this column is going to be called CH for capture history. And the separator between these columns is going to be, there is nothing separating these columns. So they're going to be next to each other without any space or tabulations or anything. Okay. And then we have another column in this data frame, which is number of individuals with this particular capture history. And this column is going to be called FRAC. Okay. So this is our new data frame, GIZ. You can have a look at the first rows of this data set. So you see that you have only two columns, CH for capture history and FRAC for the frequency, the number of individuals with the particular capture history. So we have 62 individuals with this encounter history, and so on. Good. So like yesterday, we process the data first. This is a way to tell our mark which model we're going to use, the number of observations, and so on. So we're going to use the dataset GIZ, which we just created. So in this dataset, we have the number of individuals, number of sampling occasions, and so on. And now it's no longer the CGS model. It's now the model, the class of models called multistrata for multisite or multistate, right? And this is stored in this object, GIZ.proc. Then we need the design matrix. So we just apply make design data. Okay. And we need to define some effects for the parameters. Okay. So now, remember yesterday for the Cormack-Joly-Silber model, we worked out time effects, constant effect on the survival and detection probabilities. So there are two new things here. We might have a state effect or a site effect. Parameters may differ from one side to the other. Okay, that's the first thing. And the second thing is that we have a new type of parameter, which is the transition between the sites. Okay, so we're gonna deal with this. We start with something simple, a constant survival. So this is a phi, which is a list with a formula tilde 1. You remember 1 is the intercept, constant parameter like when you call LM or GLM in R. And you may want to assess the effect of a site, the quality of site, for example, to on survival. So we're going to use this keyword stratum, which is a predefined keyword in R mark, which is going to apply an effect of the site or state on the parameter you're looking for. So here it's the survivor. Then the detection probability for our first model, we're going to consider it constant, so an intercept here. And this is where it gets a bit more tricky, is for the transition probabilities. So the transition probabilities, what we want to have the probability of going from A to B different from the probability of going from coming back to B to A. There is no reason to assume that the transition probability from A to B is the same as the transition probability from B to A. Okay, the probability of going has no reason to be the same as the probability of coming back from side B. Okay, so we're going to use some sort of interaction between stratum. So it's the stratum of departure, and to stratum, it's the stratum of arrival. Okay, so we consider an interaction between the stratum of departure and the stratum of the site of arrival. Okay, so this syntax is a bit awkward the first time you see it, but then you get familiar with it and you use it without any problem. And we remove the intercept because it's easier to interpret at the end in the outputs. And there is this this option here, this parameter link for link function, and we use a multinomial logit function, which generalizes the logit link function we talked about yesterday, in the sense that each transition probability has to be between 0 and 1. So that's the same thing as survival and detection probabilities that we discussed yesterday. But there is an extra constraint on these transition probabilities. They need to sum up to 1, because the probability of going from A to B plus the probability of staying in A has to be 1. Okay, you can leaving from A, you have only two options: either you stay on A or you go to B. Okay, and these probabilities have to sum to 1. This is the two only options you have: stay on A or leave and go to B. And so these are two exclusive events, and they need to sum up to 1. So this is what the multinomial logit link does. It ensures that the transition probabilities are between 0 and 1, and that the sum is 1. Okay. And then you apply mark. So again, this function mark that calls the software mark from R, and it's just in the model parameters here that you have a list now with 3 parameters. You have the survival. So you see that there is a difference with this CGS model. The parameter for survival is capital S now, big S. For P, it's the same. And for psi, the transition probability, it's capital P and then lowercase si, right? Careful with that, because if you are being case sensitive, if you don't use the right capital and lowercase, it will give you an error. And so we say, okay, the first model we fit is the model with a site effect on survival, constant detection probability, and transition probabilities that are, well, site-specific in a way. Like yesterday, we get some outputs, which I won't go through in detail, but you are reminded the model you fitted by RMark. You have 10 parameters. And then what else? And you have the AIC, and you have the parameters you estimated on the link of the on the scale of the link function. Okay, so for the survival, it's on the logic link scale. For the detection probability, it's also on the scale of the logic link function. And for the transition probabilities, it's a bit more involved because it's on the the scale of this multinomial logit function. Okay, but in total, what we have is we have 3 parameters for survival because we have the 3 sites. So we have a survival different from one site to the other, plus a single detection probability. We didn't distinguish a detection probability from one side to the other. We could have done it, but we didn't here. This could be another model. Huh? So 4 parameters plus for the transition probabilities, we have the transition probability from 2 to 1. Okay, so it's coming back to 2 to 1. And then from 3 to 1, sorry, from 1 to 2, from 3 to 2, and then from 1 to 3, and from 2 to 3. Okay, and you can see that there are some transition probabilities missing. These are the probability of staying on site 1, staying on site 2, and staying on site 3. Like I said, because the sum of these probabilities should be 1, the probability of, so which one is it? From 2 to 1, to get the probability of staying in site 1, you just have to do 1 minus the probability of going to 2 plus going to 3. We'll have a look to that in a minute. Huh? Okay, these were the estimates on the scale of the link function that are the link functions that are used for each parameter. Now we want the real estimates after back transformation, which are easier to interpret. So this is what we get by using the real, by extracting the real estimates. So for the survival in each site, we get a survival of 67 on the first site, 68 on the second site, and 63 on the third site, okay, with some standard errors and some confidence intervals. Okay, so the differences are not that big, except maybe on the third site. The detection probability is around 40%. And now we can have a look to the transition probability. So you see that, okay, where are we? Okay, so it's a long list of parameters, and actually this one it's always the same because there are many more parameters below here. So we're gonna do something to kind of clean up a bit the outputs, because you have if you do it yourself, you see that you have many more rows to these outputs. So we're going to use a function of rmark, which is called a few functions from rmark, 2 functions to be exact. Get real, which extracts the real estimates from the outputs you get from rmark. So we take the object we created by running mark, and we extract the psi parameters. Okay, and the VCV it's for the variance covariance matrix. So in a word, what you want here by using this true option is to get the standard errors. Okay, if you specify false here, you won't get the standard errors. So let's specify true. We extract the real estimates of the transition parameters from the object that we created by calling mark in R. Okay. Then we extract the estimates from this object we just created by extracting the real estimates. And then we apply this function, transition matrix, which briefly speaking, just clean up the outputs for specifically the transition estimates, probability estimates, because we have many of them, because there are 3 sites plus you have the, by default it gives you the time effects. Even if you don't have a time effect, it gives you a time effect. So it's kind of an ugly output. And by using these 3 lines of codes, you kind of clean up the outputs. And this is what we get. We get a transition matrix like that. So this is transition from, so it's from site, it's the site of departure from site 1 and the site of arrival in columns here. So for example, here, it's the transition probability, the probability of moving from site 1 to site 1. So it's the probability of staying on site one from one sampling occasion to the other one. From 1 to 2, from 1 to 2. So it's moving to site 2 when you start in site 1. And this is the probability of being in site 1 at time t and moving to site 3 at time t plus 1. So you see that this probability, the probability of going to site 3 is very low in comparison with moving to time 2 or staying in site 1 if you were in site 1 at the time before, at the sampling occasion before, right? And this pattern for site 3, which tells you that site 3 is not very attractive, is true also for site 2, because you see that if you are in site 2 at time t, the probability that you go in site 3 at t plus 1 is almost 0 again. Okay, so site 3 doesn't seem to be very attractive. And when you are in site 3, the probability that that you stay in site 3 is 66%, which is much lower than the probability of staying in site 2 or staying in site 1, right? And then you can get, by using these 3 lines of code, you get also the standard errors, and so this is the lower confidence bound for the confidence interval for each transition probabilities. And also there is below here, there is also the upper bound of the confidence interval for these transition probabilities. So now you can run another model saying, okay, we had an effect of site on survival in the model we just fitted. And I'd like to know whether there is actually a site effect on survival. So I'm going to run another model where I don't have the site effect on survival. And I'm going to use AIC to compare the two models, right? So let's fit that model again. Let's fit this new model where survival is just constant and there is no effect on sites on survival. And you get some estimates. And again, you get an estimate for detection probability. You get estimates for the transition probabilities. And you see here, those ones are equal. This is actually the probability of going from 1 to 2 for various time occasions and various ages. But because everything is constant, it's just repeating the same value again and again and again. And then it's from 1 to 3, you see, and then and so on. And the main difference with the previous model we fit is that now we have only one estimate for survival, because we said, okay, it's constant over, it's constant from one side to the other. And this survival is 67. And the question is this model better than the other one? Okay, we can get the transition matrix estimates, the transition probability estimates, and so on. And we calculate the AIC for both models, the one where we have a site effect on survival and the one for which there is no effect of a site on survival. And we get a difference of AIC of, you see, the model where we specify site effect on survival has a much lower AIC than the model with a constant survival. It's a difference of 15 units in AIC, right? So there seems to be definitely an effect of site on survival, and survival seems to differ from one side to the other. And that's the end of this live demonstration. And to finish, so this is the end of this lecture on the estimation of demographic parameters. And to finish, just very few kind of pointers to some papers to read and books to read. So there is this this nice paper I cited earlier about the Cormack-Joly-Sieber model and the first introduction of AIC in ecology, to my knowledge. It's this monography by Le Breton, Burnham, Claubert, and Anderson, modeling survival and testing biological hypotheses using marked animals. Like I said yesterday, it's a monography, so it's a kind of a 60 or 70 page long paper. but it's a very interesting read. So go and read it if you have time. If you you won't lose your time. There is another paper by Jean-Dominique and colleagues about multistate models. So this is modeling individual animal histories with multistate capture-recapture models. It's also a very nice paper. If you click on the link here, it will send you to the paper automatically. Yeah, you see. Okay. Like Aurélien said yesterday, this document, well, this book, let's say a book, it's an unpublished book, but a very, very useful book by Evan Couch and Gary White, who is the creator of Mark, is much more than just an introduction to the program Mark. It's also a very nice and friendly introduction to capture-recapture analysis. So if you have if you need anything with this, if you need to go really deep into a capture-recapture analysis, I strongly recommend that you have a look to the book. You can download the whole book, okay? Or you can also download chapters separately. And it's a very, very nice introduction to capture-recapture data analysis. There is a big book by Williams, Jim Nichols, and Mike Conroy, Analysis and Management of Animal Populations. When I say a big book, it's like, I can't remember how many pages there is, but it's a very, very good book. And oh yeah, about goodness of fit tests for open population models, there is this paper by Roger Pradel and two other authors, Principle and Interest of Goodness of fit tests for multistate capture-recapture models. And you have a synthesis of goodness of fit tests for the COMAC and also multistate models. And the paper is open access. And I think that's all for me, yeah? So, yeah, so it concludes the lecture on estimating demographic parameters. So we're going to take a break for, let's say, times it 20 to 10. So we're going to take a 20-minute break and be back at 10 a.m. for another lecture now on population projection models that Sarah will give. And okay, so have a nice break, coffee or whatever. And let's be back in 20 minutes, 10 a.m., right? See you.
Hello, everyone. So we're back. And now I'm going to share my screen. Up, should be okay. Okay, so thanks, Olivier, for a great class on demographic parameters. And now we're going to move on to population projection models together for the next classes, actually. So we've seen with Aurélien yesterday how to assess population abundance in class 1, and then with Olivier how to estimate demographic parameters and identify the causes of variation in demographic parameters. And now we're going to go through together what we can do next, which is evaluate population viability to inform decision about management actions. So one of the main reference on population viability analysis is a handbook, a practical handbook for population viability analysis from Maurice and his collaborators. And in this handbook, they give a definition they give the following definition for population viability analysis, which I'm going to call PVA in what follows, because it's going to be easier for me. So it's the use of quantitative methods to predict the likely future status of a population. And they're really clear about the fact that it's tentative assessments based upon what we know, which is frequently imperfect and incomplete. So it's obviously not ironclad predictions of the population fate. So we should always keep this in mind in what follows. And despite this, PVA can be very useful because they allow us to quantify rate of population change over time. We can also use them to estimate extinction risks, which are used, among others, by the IUCN to define population conservation status. And also we can use PVA to identify key parameters for population management and even compare the relative impact of different population management actions on the population dynamics. So we'll see how we can do these different things together. So one way to run a PVA is to use population counts. Like you talked about this with Aurélien in the first class. So we can run a PVA based on population counts gathered from the field. It's called a count-based PVA. So imagine a population that follows an exponential growth. I don't know if you can see my mouse. Yes, probably. Yes, okay. Imagine an exponential growth of a population, which is constant over the years. So here it's population size. We can define a quantity that is called the population growth rate and denoted lambda, which is equal to the population size at t+1 divided by population size at times t. This quantity, lambda, the population growth rate, gives the proportional change in population size in time. So if lambda is bigger than 1, it means that the population is growing. If lambda equal 1, then it's a stable population. And if lambda is lower, less than 1, it means that the population declines. So if this population growth rate is constant, like for the 3 populations simulated here, after t time steps or t years in general, we can calculate the population size nt, which is equal to initial population size at time 0 multiplied by lambda to the power t. Okay. So this quantity lambda allows to calculate the predicted population size at any given time step using this equation. So lambda is distributed following a log normal distribution. So we can write this down like this: population population growth rate follow a log normal distribution with a mean mu and a variance that we can call sigma 2. So it's easier to work with the intrinsic rate of increase, denoted R, which is just simply the log of lambda. So you take the log of the ratio of population size at t+1 divided by population size at time t, which we can also write log nt+1 minus log nt. It's the same thing. And this quantity, the rate of increase, is normally distributed. So it's much easier to work with normal distribution because we know how to work with that very easily. It's the mean of the rate of increase is mu, and sigma 2 is called the environmental variance. So the variance of the rate of increase. So we can estimate these two quantities on using our data. And if the mean rate of increase of the population is less than 0, we know that extinction will certainly occur. But if the mean rate of increase is positive, extension can still occur if environmental variance is big enough, I was going to say. But in other words, variable environments increase the risk that a population can go extinct. Even if, in average, the population is growing, the variability in the environment can drive the population to extinction. So we're going to take an example, the example of the grizzly bear population in the Yellowstone National Park. It's from Morris and Doak in 2002. So here is population size between the 1959 to 1997, and you can see that the population is growing for this part quite exponentially. And we're going to try to run a PVA on this data. So I'm going to go through the code here, and then in the live demo, we will try to run it together directly in R. So the first step is to use the population count data to calculate these two quantities, mu, the mean rate of increase of the population, and environmental variance, sigma 2. So as I just said before, you need to take the log of population size at time t+1 divided by population size at time t. In R, it's the same thing than taking the vector of population sizes minus the first value divided by population sizes minus the last value. Minus, I mean taking out the last value. So it's going to give you here nt+1 at each time step divided by nt at each time step. And mu, the mean rate of increase, is simply the mean value of this ratio, log ratio of population sizes. And we can calculate the variance with the function var, which gives us the environmental variance. So mu here is 0.02, a bit bigger than 0. So the population is growing in average. And sigma 2 is equal to 0.013 about, which reflect a rather low year-to-year environmental variance. Okay. In the case of this example, we had one population count per year. So we can just calculate the mean and variance of the log ratio. But in certain cases, people have unequal time intervals. So population counts every 6 months and then 2 years. So in this case, you just need to calculate the square root of the ratio of population size at time t+1 divided by time t, and divide the log ratio by this quantity, okay? So x here is the square root of the duration of each time interval. To get mu and sigma 2, you need to run a linear model of the log ratio of population size as a function of the duration of each time interval, the square root of each time interval, forcing the regression to have a zero intercept. This is just a way to calculate mu and sigma 2 when you have an equal time interval. So it's a bit less straightforward, but you can easily do it. So we end up with the same value of mu, which is the slope of the regression we just did, and give you the mean rate of increase. To get the estimate of sigma 2, we perform the ANOVA, the analysis of variance of the model, and the environmental variance correspond to the residual mean square value of the ANOVA. So we end up with the exact same value than before in this case because we had equal time interval. We can estimate confidence interval on mu, the mean rate of increase, and we see here that even if the mean rate of increase is positive, if we consider the confidence interval, so 95% confidence interval, it encompasses 0. So we cannot rule out potential risk of decline for this population. And this is because of the environmental variance. So we can also calculate the confidence interval for sigma 2, and it goes from 0.008 to 0.021. So it's bigger than 0, which means that environmental variance here is not null. So if we back transform the finite, the mean rate of increase, so if we take the exponential of mu, we end up with the population growth rate. So the lambda is equal to the exponential of mu, which makes sense because it was just a log transformation. So lambda is bigger than 1.02. So in average, the population, the grizzly population is growing, but we remember that it doesn't rule out the possibility of a decline because of the environmental variance. So now that we calculated mu and sigma 2, we can try to project the population in the future. So using the equation that I exposed before, the number of individuals in the population at time t is equal to the initial population times. So if in this first step we do not consider environmental variance and try to run a very simple model, we can just use the mean rate of increase of the population to project the population in the future. So here we are just considering that there is no environmental variance. Each year, the rate of increase of the population is exactly equal to mu. So in the log, if we log transform this equation, it's easier in terms of programming because we get rid of this exponential here. The log of population size at time t equal log of initial population size plus mu, the mean rate of increase, multiplied by t, the number of time steps we want to project the population over. So we need to know the initial population size, which in the case of the grizzly population was 44 individuals in 1959. We want to project the population over 38 years. That was to get an estimate of the population in 1997 so that we can compare our projection with the actual data. And we just calculated mu, the mean rate of increase of the population. So using these quantities, let's project the population using the equation that I showed you just before. So we end up with this projection, population size here as a function of years. In red, you have the actual data, the population counts of the grizzly in Yellowstone, and the projected population size in blue here. So you see that it's a straight line because we use a constant mean rate of increase, mu. And you can see that in average, the projection is not doing so bad because in 1997, we end up with the exact same population size than what is really observed on the field. But we see that over the years, the prediction is quite far from the actual data. So here in this part, we're overestimating the population growth because the slope of this blue line is higher than the actual data. Here, the population was a bit declining and then quite stable. And then in the actual data, we see an exponential increase with some variability around from the 1980s. So in this part of the model, we're still quite far from the prediction, and we underestimate the population growth because here the slope is actually higher than here. So our projection here is not doing very well. Why is that? Well, it's easy. We just considered that the population growth rate was constant over the years. So that's really not recommended. It's a very simple model, but you're missing a big part of what's happening in the field most of the time, okay? So what we want to do, if we can, is to account for observed variation in growth rate in the projection. So first, we need the initial population size, the number of time steps we want to project the population over. So we used 38 before, but now we can try to project a bit further in time so that we can look at our predictions in the future once we have no more data and see what the projection predicts. And then we will be able to compare this to to use these predictions to calculate extinction risk, etc. Because we include some temporal variation in growth rate, there is some stochasticity in the model, some random variability. So we need to repeat our simulations a certain number of times so that we get some confidence intervals around the mean prediction. As a function of environmental variance, the confidence interval will be wider or less wide if environmental variance is lower. So we need now to create a matrix to store our results because we're not going to run just one simulation, but 500 simulated populations. So we're going to store these 500 simulations in a matrix with T rows because we project over 50 over T time steps, and 500 columns because we simulate 500 population runs. We initiate the simulation by giving the value of the population size at time T at the first time step. So the first row of the matrix will take the value of the initial population size. Now we need a new to set a new quantity. If we want to estimate extinction risks, we need to define what is the threshold for minimum viable population that we consider. So this threshold can simply be one female or two individuals, but it can also reflect a minimum viable population that we consider is the minimum number of individuals so that the population can persist, given that there can be genetic drift, demographic stochasticity, etc. So in this case, we're going to consider that 30 grizzly bears is the minimum viable population size for this example. So this number is defined based on the biological knowledge that you have of the species that you're working on, okay? Okay, so in general, we can take this, we consider a minimum viable population size, because if just one individual is left in the population, it's really hard to do anything to prevent extinction. So now we're gonna run the projections. So we need to loop over the number of repetitions. So I here will go from 1 to 500 runs. Then we do a second loop over the number of time steps. So here we want to project the population over 50 years. So big T here is 50. Then at each time step for each run within the loop, we're gonna draw a value of rate of increase for the population from a normal distribution with a mean value equal to mu and a standard deviation equal to the square root of the variance sigma 2 that we estimated from the data. So this part is really important because it's here that instead of just using a constant rate of increase of mu, every year we draw from the normal distribution a different value of mean of rate of increase R, taking into account the environmental variance that we estimated from the data. So each year we're going to have a different value for lambda, which is equal to the exponential of R, and we use this value of lambda to calculate the population size at t plus 1. So n at t plus 1 equal n at time t for the run I, because we repeat this 500 times, multiplied by the value of lambda calculated for this specific year in this specific repetition of the simulation. And that will give us the number of individuals in the population at t plus 1. Then we set an extension threshold. So if population size that we just calculated at time t is equal or less than the extension threshold, so the minimum number of individuals below which we consider the population is going to go extinct for sure, then if n at time t is less than this quantity or equal to this quantity, we specify here that we consider that the population is going to go extinct. So n is going to be equal to 0, and we move on to the next population run, to the next run, okay? Wow, not so easy to explain. Here is the results. Let's go back to something a bit more concrete. So that's the log of the population size for each one of the 500 populations that I just simulated for the grizzly bear. So here we're in 1959, 38 years after it's 1997, so where we had our last population count. Sorry for this internet problem. And we clearly see that including environmental variance in our simulation give a very diverse population trajectories over the 500 populations. So here would be the average population prediction with a lot of different trajectories depending on environmental variance in the population. So we can look at the population size distribution at the last time step over these 500 repetitions. And we see that many populations are around a few number of individuals, 100 something individuals. Some of them, many of them, over 100 population repetitions got extinct with a last population size at the last time step, which is equal to 0. And a few population grew very, very fast and have very high number of individuals in the population. That's because of the random subsequent occurrence of low or high values of environmental variance. I mean, this population, just by chance, they had very big value of the rate of increase in subsequent years. So they ended up growing very fast. But many of the populations are below 500 individuals at the end of the simulations. So another way of looking at the results is to plot the log of population size, the average value of our prediction in blue, which is the blue line. The gray, shaded gray area represent the 95% confidence interval calculated over the 500 repetitions. And the red points here are the population counts, the data. So we see that on the log scale, we are not so far away if we look at the mean prediction compared to the data. Okay, but there is a lot of variability around this mean prediction. So the average population growth just by itself doesn't do a good job at predicting what most population realizations will do, because there is a high variance between the different population trajectories. So it's easier to calculate the extinction risk and the time to extinction to have clearly in mind what are the chances that the population will go extinct at various times. Okay, so in general, we are really interested in these quantities, because just looking at a graph like this doesn't tell us directly how many of these populations, of these 500 populations, will go extinct. What's the probability that the population will go extinct? So to calculate the ultimate extinction probability, so the percentage of trajectories over the 500 here, that will reach the extinction threshold before the end of the simulation. So in our case, it was in 50 years. It's gonna be the sum of the number of population trajectories for which the last value of population size in 50 years is gonna be lower or equal to the minimum viable population size threshold that we defined, divided by the number of runs, because we want to calculate a probability. So the number of populations that got extinct over the total number of populations that we simulated. For the grizzly bear, the ultimate extinction probability over the 50 years is about 22%. So you see that is not so low, And we can look at the cumulative extinction risk over the years. So starting in 1959, if we calculate the probability of extinction each year, we can look at how it's gonna change over the years. Looking at the mean value, and the gray area here is the confidence interval over around the mean value for the extinction probability. We often call it quasi-extinction probability because we consider an extinction if population size is below the quasi-extinction threshold, so the minimum number of individuals that we consider is needed in the population to prevent extinction. So you see that for the grizzly bears, it's going over 20% and reach 22% in average at the end of our simulations. We can calculate some summary of the extinction probability. We don't want to use the mean time to extinction because of the few populations that grow very fast. If we just look at the mean value of the time to extinction, it's going to be an overestimation. So we prefer to calculate the median time to extinction. because it's less the median is less influenced by the few trajectory, the few population trajectories that will go very fast, grow very fast, and have very big number of individuals at the end. So better to use the median time to extinction. So how we can calculate it? We create an empty object to store the results that we can call max t. That's going to be the maximum time to extinction. We're going to write a loop over each repetition. So 1 to 500 populations simulated in our case. N number of individuals in the population for each run. Okay, so here I take the run I of my simulations and I call it N so that I don't have to repeat this name, or it's easier to give it a different name. And I'm gonna calculate here at what time step N population size for this run was so at which time step the number of individuals in the population was still bigger than 0. So the population was not extinct, and I'm taking the value of the maximum time step at which the population was not extinct. Okay, so what I'm gonna have here is the time at extinction for the population that went extinct. So in this vector here, I store the maximum time before extinction. I hope it was clear because I don't feel like it. So I can take the median value of this vector, which is giving me the median time to extinction for the population that went extinct in the simulation. So here, this median value is equal to 11. So 50% of the population that did go extinct in the simulation did so before 11 years in the simulations. So it's quite fast. Here we can plot the time to extinction for each of the population that went extinct in the simulation. And in red here, we represent the median value. So 11 years is the median value of the time to extinction. So it's very interesting to evaluate the sensitivity of these results if we change the initial population size. We can also vary the extinction threshold and see how extinction probability and time to extinction will change. Also, of course, vary the amount of environmental variance, which has a big impact on the results. And also change the number of time steps in the simulation. Here I projected over 50 years, but we should keep in mind that projecting the population over a bigger number of years is we are making a lot of assumptions about what will happen in the future. Okay, because here I assume that over the next 50 years, the amount of environmental variance in the data, in the projection, will be the same than what I observed on the field. So the more you project over a large number of years, the more you have to be confident about the assumptions that you're making. So let's try to do it in R with the live demo on the grizzly bear. So first, we want to load the package PopBio. Est-ce que je peux maybe make it big enough so that you can read properly? So you have this code under the live demo in the website. So first we load the package. And in this package, the grizzly data are included, so we can view the grizzly population counts. From 1959, we had 44 individuals to 1997, where there was 99 individuals in the population. Okay, so we're just gonna rename the data, and it's going to be population counts observed on the field, and we create an object that we call years with the years at which population counts were measured. We can have a look at the data. We need to load the ggplot package so that we can make graph. ggplot2. Okay, so now I should be able to plot the data. Okay, so it's the same. We see from over 40 individual, quite stable with some variability, and then exponential growth in the population from the 80s to reach about 100 individuals at the end of the 90s. So we first calculate the log ratio of the rate of increase at each year. So if we take the population counts minus the first value, so starting in 1960, divided by the population counts without the last value in 1997, it's giving us NT plus 1 divided by NT, so the rate of increase, the growth rate at each time step, and we take the log of this ratio. So we calculated here log of NT plus 1 divided by NT every year, log of the ratio of population size. If we take the mean value of the log ratios, it's giving us the mu, the mean rate of increase for this population, 0.021. We say the population is growing in average. The variance of the log ratio is giving us the sigma 2 quantity, which is equal to the environmental variance calculated from these counts. So the average population growth is equal to exponential of mu. So lambda, oops, what happened? Sorry, up. Okay. So lambda is equal to 1.021. So in average, the population is growing. So let's project the population. So initial population size is, we take the first value. So 44 bears in the population in 1959. So I want to project the population starting from here over 50 years. So that's big T. And let's do 500 repetitions. So you don't want this number of repetition to be generally, it has to be at least 500 repetitions, and 1,000 repetitions is good too, is better, but 500 is okay here. So the more the number of repetitions increase, the longer it will take to run the simulation. But here is very fast, so it's okay, no problem. So we're gonna do 500 runs and create an empty object to store the results. So if you want to look at this object, this matrix filled with NAs, is just NAs over 500 columns and T rows, so 50 rows. Up, if you want to make sure of it, you can ask R to give you the size of this matrix, and it's 50 rows and 500 columns, so that we are sure we can store in this object every population size in our simulations. So we want the first row of this matrix to be equal to initial population size, which was 44 individuals in the population at the first time step. We set then the extinction threshold. So we said that we consider 30 grizzly bear to be the minimum viable population. So NE equal 30. And now we can project the population. So we want to run 500 simulation over 50 years, and we can see what this function is doing when we draw the mean rate of increase from a normal distribution up. If we look at this part, is just drawing one value from a normal distribution with mean mu and standard deviation square root of sigma. Okay, so every year for every simulation, it's going to draw a different value for the rate of increase. So let's run the simulations up and look. So you see it's quasi instantaneous, and we can look at the results. So for each of the 500 simulations in column, we have population size starting from 44 for every run. And then we have the projected population size for this given simulation over the 50 years. So we see that this first trajectory is increasing up. And at the end of the 50 years, we end up with 142 individuals in the population. And obviously, the results are going to be different for every repetition, because we draw randomly from a normal distribution every year for every run a different value of R, of variability around the mean rate of increase. Okay, so let's try if we find some, let's see if we find some populations that got extinct. Yes, so the 10th repetition, you see that at time, where are we? Time 15, 16, up, this population got extinct because in between here and here, population size went below the threshold that we set to 30. So the population is considered extinct. So it remains to 0 until the end of the simulation. Okay. So let's plot all the population trajectories. So the 500 repetitions here over the 50 years. Okay, so that's the log of the population size. And we can specifically look at population size for these 500 repetitions at the last time step. So I'm just looking at the last row of the big matrix. Okay, I'm going to have 500 values for the last population size. And I can ask R to give me a summary of this vector. So minimum is 0. The biggest population is 1,000 and almost 800 bears, so that's huge. The median is 112. Okay, let's plot this. So that's the same thing, population size at the last time step of the simulation, with the few populations that grew very fast and very big, and most of the population here, many that got extinct, and the others that are below 500 individuals. So I can calculate mean population size with the confidence intervals to draw the plot. So I'm calculating here the confidence, 90% confidence interval from a normal distribution. So that's the usual way to calculate confidence interval from a normal distribution with the 1.96 value up. I'm making a data frame, storing the number of years, the mean population size with the confidence intervals. And I also want to compare it with the actual data. So I include it in the data frame too. And I can plot this now, which is giving me the projections, mean value, mean population, projected population size in blue with the confidence interval, and in red, the actual data. I can now calculate the probability of extinction but you see we were 22% in the slides, and rerunning the same simulations, we are at 19% after 50 years, okay? So we might want to increase the number of repetitions to 1,000 to have more reliable results, because with 500 runs, it changes a bit. We can calculate the cumulative distribution of the extinction probability using this function, XCDF, so to get the cumulative distribution. The arguments are mu, the environmental variance, the initial population size, and the extinction threshold. We calculate confidence intervals for this function, and we can extract the mean cumulative extinction risk with the confidence intervals and plot this up over the years, okay? And then we can look at the time to extinction, and I'm gonna go fast now because it's time for a break. Look at the time to extinction. So here the median time to extinction is 12 years in our simulations, and plot the time to extinction with the median time to extinction in red here. So it went from a few years, like 3 years, some populations got extinct, until that must be around 40 years. Okay, so that's the time at which every population that got extinct in our simulations. Okay, that's it. Let's have a break and start again at 11. See you. Okay, so let's start again. I'm gonna share the screen. So we've seen in this part how we could run a simple population viability analysis based on population counts. So this approach has several limitations. The first one is that we are considering that the counts that we get from the field represent population size exactly. So we are not trying to include in there some sampling error or problems of detectability, like what you discussed with Aurélien and Olivier. Okay, so that's a big limitation. So it's working well if you're quite confident that the counts that you have for this species is a good indicator of actual population size. Also, in this simple model, it's assuming that the population growth rate is exponential, so there is no density dependence. There are some variants of the count-based PVA which exist to include the density dependence in the models. We just don't have time to go through it here, but it's possible to include it in there. And the only source of variation in this version of the PVA is environmental stochasticity. So we did not consider in this analysis demographic stochasticity, which is the fact that every individual just by chance can survive or die, even if the average survival probability is the same. Just some years randomly, all individual can die or more can survive. And demographic stochasticity has a big impact on the extinction risk of small populations. Okay, so if you're working on a population with reduced population size, it's better to use a model which include demographic stochasticity. And also, the way that we included environmental variance here was considering that there is no trend or change of the mean environmental conditions during the projection time, so that there is no environmental change, or there is just some random variability from year to year. And we considered that the environment was not correlated among successive years. Whether we know in some cases that it's for some species, the consequent bad years following each other can have dramatic consequences on population viability. Okay, so it was a very basic model, but the principle of population projection is in there. And you can complexify the model if you need, based on your specific case. So here it's working well if you have moderate environmental variability. And an advantage of this model is that they're very simple. You just need to have population counts for at least 10 census occasions, 10 years. And as you saw, the calculation is relatively easy to do if you know how to use R. And these simple models work quite well when the assumptions are met. So when the population is growing exponentially, if you have no density dependence, and if you can ignore demographic stochasticity, which is generally not the case for small populations. And what is really relatively nice is that you can try to assess the quality of your model by hindcasting. What we looked at when we plotted the projection versus the data together with the data, we can see that the mean projection was relatively close to the observed data, which is an indication that our model was working relatively well. Not like in the first case, when we did not include environmental variance, we saw that the mean trajectory was relatively far away from the observed counts. Okay, so it's an interesting approach, but there are some limitations because we do not get at demographic rates here. We just use population counts. If the only thing you have from the field, then you have to make the most of it. So it's good to be able to run projections using only population counts. But lambda is only giving you a summary of the population dynamics. Is it growing? Is it declining? But there is no information about the mechanisms that govern the population dynamics. Okay, for this, we have to get at demographic rates, what we're going to do now. Okay, if you just use lambda, it doesn't give you any hints for which parameter, which vital rate or demographic parameter is most important for population dynamics, and on which parameter is it better to act if you want to protect a population or manage a population. Okay, is it better to try to increase adult survival, fecundity, survival of juveniles, etc. So now we're going to see how we can assess population viability from demographic rates this time, so that we can look at the mechanisms that govern population dynamics. So I'm going to present matrix population models, MPMs, and how we can use fertility, denoted F, and survival, S, rates to project the population. So to keep things relatively simple, we're going to assume for now that there is no migrations. So survival and fecundity rates are the demographic rates that govern the entire population dynamics from one time step to the next. So population size at time t+1 can be written as the number of new individuals produced in the population through reproduction. So number of individuals at time t time fecundity rate plus number of individuals at time t that are still alive, so times survival probability. And this equation is completely summarizing the population dynamics. The problem is that, as you saw just before with Olivier, demographic parameters are often heterogeneous across the life cycle. So it's for most species, survival rate and fecundity rate change with age or with stage, like juvenile, adult, subadult, etc. during the life cycle, during the life of individuals. So the cases where we can consider that this equation work well are relatively not so frequent, because all individuals do not share the same fecundity rate and survival rate. And that's why matrix models are very interesting here. Okay, so the purpose of matrix models, matrix population models, is to incorporate vital rates that are heterogeneous across the life cycle. And using these age-specific or stage-specific vital rates, we're going to project the population using the demographic rates of individuals. So let's take an example, the barn swallow, with a life cycle that is not so super easy, but can be simplified for the purpose of this example. So the swallows migrate in autumn to reach tropics area during the winter. So in autumn, they gather in flocks in fields. We can see them in Europe, and then they go in the south, in the tropics during the winter. They come back in spring before reproduction. In March, April in France, we can start seeing the swallows around. And they reproduce and raise 2 or 3 clutches during the summer in France. Okay, after reproduction, once the young of the year are raised, are independent, they spend the summer here, and then will migrate again in the next autumn. Okay, So let's consider for now that breeding occur here in May in France. So if we want to describe the life cycle of the species, previous studies have shown that chick survival that we can note S0 is different from juvenile or yearling survival S1, and that it's also different from adult survival that we can call S2. So, okay, so we have 3 age classes to describe individuals in this population. Concerning fecundity, we need to consider 2 parameters: F1, which is fecundity of juvenile yearling females, and F2, fecundity of adults. I'll get back to that later, but in these models for now, or for now, for all day, we're just going to consider one sex model. So we consider that females drive the demography, which work pretty well for all species that have balanced sex ratio, and that the females produce the young. Okay, so if you model the demography of the females, it's enough to consider to get at the population dynamics. You just consider that the total population is number of females times 2. Okay, it's quite important because here the parameter F, fecundity, is for the number of females produced by a female. Okay, so you take the number of egg or offspring produced by a female and you divide it by 2 because you just want to count the number of females that are produced. Okay, so using these 5 parameters, we can model the life cycle of the swallow. An important question is, what is the timing of the data collection compared to the breeding season? Swallows reproduce all at the same time, so it's birth. It's what we call a birth pulse reproduction. So at one time of the year, all individuals reproduce at the same time. Okay, the breeding season is in June in France for the swallows. So if we come to monitor the population before the breeding season, we call it a pre-breeding census. Okay, so if we want to represent the population dynamics at this time of the year, before the breeding season, it's quite different from a post-breeding census if we come after the breeding season. Okay, let's first consider that we come before the reproduction. Okay, so if we come before the breeding season, we're not gonna observe chicks in the population. So we will model the population dynamics of 2 age classes that we can observe in the population before the breeding season: the juveniles and the adults. A1 for the juvenile, A2 for A2 plus individuals that are 2 years or more. Okay. Then the breeding occurs, the newborn chicks are produced, the A0, but we do not observe them directly. So what can happen between year T and year T plus 1 when we come back to census the population? Well, the juveniles can survive with survival probability S1 and they will become adults. The adults, they can survive with probability S2 and remain in the A2 plus age class. Okay, that's for the survival part. What about reproduction? Well, the juvenile, just before the breeding, they are able to produce offspring when they're juvenile with fecundity parameter F1, so they'll produce some newborn, and the adults too with fecundity F2. The newborn that we do not observe directly, they can survive with probability S0, and they will be juveniles when we come back on the field next year and we observe the population. Okay, so all these different flows of individuals can happen in the population in between two census occasions. So this little graph is very useful when you try to write down the life cycle of your species. It's really a way to model all the flows of individuals that can happen and to avoid making mistakes at this first step of writing down the life cycle. Okay. So, as I said before, in a pre-breeding census, we do not observe newborn directly. D'accord? So we just observe them once they became juveniles. So we do not observe the one that have not survived. So now the second step is to translate this agenda of events into a life cycle graph that is also called a Caswell representation, in which we have two circles here that are the categories of individuals in the population. So we said that we do not observe directly the newborns, so we just have the A1 and A2 plus, juveniles and adults. And we're gonna represent the demographic flows on the life cycle. So I'm using this graph to make sure that I do not make any mistakes in the arrows that I want to represent. So the juveniles, they're coming from, with probably S0 times S1, the juveniles present in the population the year before. So that's this arrow here, juveniles coming from juveniles the year before, F1 times S0. Juveniles are also coming from the adults in the population the year before with probability S0 times F2. So I'm just going back the arrows, okay? So the juveniles are coming from the adults the year before with probability F2 times S0. Okay, that's it, just two different paths for the juveniles, and the adults in the population at times t come from the juveniles A1 with probability S1 or from the adults with probability S2. So A2 come from A1 with probability S1 or from A2 with probability S2. Make sure that you did not forget any arrow and that the probabilities you write here are correct. And use this trick of coming up, following the way up with the arrows to make sure that you do not forget anything. Okay, so that's the life cycle with the demographic rates representing the population dynamics of the swallow here. We can translate this into equation, and that's pretty easy. If this step, you got this step right, it's pretty easy to not mess up the equation because you just need to read up your life cycle graph to write the equation. So number of A1 in the population at time t plus 1 is gonna be, number of A1 at time t plus 1, it's gonna be F1 times F0 A1 at time t plus F2 times S0 A2 at time t. So F1 times F0 at time A1 at time t plus F2 times S0 and A2 at times t. Okay, so I'm doing the same than before. I'm just reading up the arrows. Number of individual age 2 or plus at times t plus 1, it's going to be S1 times number of individual age 1 at time t plus, because there is a second arrow, number of individual age 2 at S2 times the number of individual age 2 at time t. Okay, so that's the second equation, S1 times NA1 at time t plus S2 number of individual H2 at time t. So I have as many equations as number of circles, which correspond to the different categories of age classes or stages in the population. The last step now is to arrange these equations into a matrix format. So I want to know the number of individual age 1 and 2 at time t plus 1 as a function of these different demographic rates time the number of individual age 1 and 2 at times t. So it's going to be f1 as 0, f2 as 0 in the first line of the matrix. Imagine here, this quantity, it's giving me the number of individual age 1, because first row at time t plus 1, coming from the number of individual age 1 at time t. Okay, and this quantity here is giving me the number of individual age 2, because it's second column at time t plus 1, coming from the number of individual age 2 at time t. Okay, so first row is a1 t plus 1, second row a2 t plus 1, first column is a1t, and second column is a2t. Okay, so it's the same order than in the equations. Okay, so you just report the demographic parameters in the matrix here. So that's taking a little bit of training, of practice before being able to go from the life cycle graph to the matrix. But if you do it carefully and putting the parameters in the same order, you should be able to do it without error. Okay, now we just need to replace with the actual values of the demographic rates. So survival of chicks times survival, which is equal to 0.2. Survival of juveniles 0.5 and survival of adults 0.65. Number of females produced by juveniles is 3 divided by 2 because we just want to count the number of females. Okay, they produce 3 eggs in average, so we divide by 2 because sex ratio is balanced. And the fecundity for adult female is 6 divided by 2, so 3 for this population. So what we have here is the transition matrix for the barn swallow in a pre-breeding census. Woohoo! Yes. So what would be the difference if we had considered a post-breeding census? Imagine we model the population just after the breeding season. Well, this time, if we are just after the breeding season, we will directly observe the newborn in the population. So now we would model 3 different categories in the population, A0, A1, and A2+. In between the 2 years, the newborn can survive and become juveniles with probability S0. The juvenile can survive and become adults with probability S1, and the adults can survive with probability S2. For breeding, and that's where it's generally tricky and people mess it up the first times, or quite often. I still do mess it up sometimes. I have to pay attention. Because the breeding season occurred just before you come back and census the population again, the newborn that you observed here, they will be juvenile before the next census. So they can actually breed and produce themselves, grow, become juveniles, and reproduce before the next census. So you do not forget these arrows here. Juveniles produce newborn with probability F1, and adults produce newborn with probability F2. So the complete life cycle looks like this. And we're gonna go up the arrows like before to write the life cycle graph. Sorry, no glass. So this time we have 3 different categories in the populations. And this arrow that can be a bit surprising at first, that chicks produce chick with probability S0 times F1, is because you are in a post-breeding census. So newborn observed in year T grow with probability F0 and reproduce with probability F1. So it's not an error that a newborn can produce newborn, because in the time that they produce newborn, they will have become juveniles. Okay. So next we write the equations. So this time we have 3 different equations, and we arrange this in a matrix format with number of individuals A0, A1, A2 at times T, giving the number of individual A0, A1, or A2 at time t plus 1. Okay, so we know how to write the transition matrix. So we might wonder, why is the matrix format interesting? First, it's easier to read than multiple equations. You know, I prefer to look at this than to look at this. It's much easier for my eyes. And imagine that if you work with a species that has a complex life cycle, or that live very long with different survival probabilities, the number of categories, the number of age classes or stages that you have in the population can increase. And it would mean that you have many, many, many equations to deal with. Whether it's easier to deal with still one matrix, but just a matrix with a bigger size, okay? So whatever the species you're working with, even if it has a complex life cycle, you're still gonna be able to write this life cycle and summarize it in a single matrix. So it's very cool. Plus, the matrix are a mathematical object, and they have intrinsic numerical features that are very useful for us in population dynamics, and we're gonna talk about this in a few slides. So, as I just said, whatever species you work with, you can write down is transition matrix. So there are big database online that everyone can access, like the Compadre and Comadre database that have been set up by the Max Planck in Germany. And you have more than 700 transition matrices for plant and tree species, and more than 400 transition matrices for animal species coming from the literature. So you have several transition metrics for the same species, depending on what people have considered the best way to summarize the life cycle in different places or different populations, etc. So it's very, very nice. I'm going to show you a few examples very briefly how we can write the life cycle when, for example, you have several sites. Let's consider the barn swallow here. They can breed in different areas. So we might want to include location A and location B, for example. So we're going to have this time 4 different compartments of individuals in the population: juveniles inside A, adults inside A, and there can be movement of individuals between the site A and then juveniles inside B and adults inside B. So you can write this life cycle in a matrix format. This time you have 4 rows and 4 columns because you have 4 classes of individuals. And we need to introduce a new type of probability in addition to survival and fecundity, which is dispersal probability. So the probability of going from site A to site B, for example. So here for the example, I just consider the dispersal probability is the same for every age and from going from one site to the other and inversely, but you can as well consider that it would vary with age or be higher from site A to site B or the opposite, okay? And that would just change this D parameter in the matrix. So you can very easily introduce, you can introduce different sites. You need to know the demographic parameters in the different sites and the movement probability between the sites. You can include, another example would be variable age at first reproduction. So that's for the slender-billed gull. You would have juvenile non-breeders that can remain non-breeders when they become adults, like age 2, or they can transition to the age class 2 breeder compartment with a probability S1 for the survival times psi for the we could introduce this probability psi to model recruitment probability, so the probability that they become a breeder. Okay, and imagine adult. So the A1 can be non-breeder or breeder, and here in this example, once you are a breeder, you remain a breeder, or you can become non-breeder. Okay, so this introduces a new probability, the recruitment probability, psi, that also can vary with age or etc. in the matrix. An example for a plant species, the peony here with different stages this time, no age classes, but stage. S1 is a seed that was produced the year before, which can remain a seed one more year or become directly a small plant, a small seedling. Okay, same for the seed the year before with a certain survival probability, and J, which would be the germination probability for a seed to become a plant. And then in this species, there are three different stages for the plant. It can be a small seedling, a tall vegetative plant, or a flowering plant. And individuals can transition between these three different stages. So it's introducing a new, different types of probability that we denoted here TXY, which represent the probability of transitioning from one stage to another stage. So in this matrix, we have 5 rows and 5 columns because we have 5 different stages. And the survival, fertility, and transition probability between stages. And some species have a much more complex life cycle, so the matrix can be quite big with different types of probabilities, but still it remains a single matrix, so it's quite handy. Okay, so to summarize this, the projection matrix, if you want to write it down for your species, you have to think about how many age classes or stages you need to include to represent the life cycle. When is the age at first reproduction? Because here is an example in which individuals can reproduce from age or stage 1, but sometimes you have some zeros here until age or stage at first reproduction. Is the maximum age at death fixed or not? Which will define the right-hand corner of the matrix. Here is an example for a species with limited growth or limited age at death. And you know that once the individuals reach the last age or stage class, they cannot survive anymore. So you would have a 0 here. But sometimes there is still a remaining survival probability, even at advanced ages. And then do not forget to think about the pre-breeding or post-breeding census, because it will control the number of stages you have in the population, whether you directly observe the newborn or not. So the matrix will look like this if it's structured by age, and we call it a Leslie matrix from the name of the guy that first invented it. Or if it's structured by stage, it's called a Lefkowitz matrix. And in a Lefkowitz matrix, sorry, you have the probability of transitioning between the different stages that you don't have here, because we all know that unfortunately, once you're a certain age, you go to the next age class the year after. Okay, so once we have the matrix for a given species, what do we do with it? Well, we can use it to project the population. Based on our knowledge of the demographic parameters, what will the population look like in the next year or the years after? So let's start simple with deterministic matrix population models. So here we will not introduce environmental variability, but just consider that the demographic parameters, they do not change in time or among individuals within the same class. So the first step is to write the matrix in R. So for the swallow, we would use the matrix function with the different cells of the transition matrix that we wrote before. We have 2 rows because we have 2 rows. So we specify that we are giving the different values by row, by the order of row. Okay, so let's look at the matrix to make sure it's correct. Okay, fine. We need to decide what's the initial population size from which we start the simulation. So here we consider that we have 50 age 1 and 30 age 2 in the population. So we create this vector containing the initial population. And we can project to the next time step using the transition matrix. So initial population size times, this is how we code a matrix product in R. So percent star percent. So if we multiply by this matrix times the initial population size, we get the number of individuals at times t plus 1. That's exactly the equations that I showed you before, how to code them in R. So you see, it's pretty easy. Just write this matrix product and you get the vector of population size at the following time steps. So 33 age 1 and 44.5 age 2 in the population. You can repeat this calculation, for example, for 10 years using the matrix power function from the package matrix calc. And you specify the number of times you want to project over. So that's raising the transition matrix to the t power, because and you multiply this with the matrix product by the initial population size. So if you remember the first equation that we saw this morning, nt equal n0 times, here it would be the transition matrix raised to the power t, the number of time steps to project over. And we get the number of individuals in each class at time step 10. Okay, so that's a bit annoying because we're doing it by hand. So there is a very handy package which is called PopBio with built-in functions to project the population over and calculate the different quantities of interest. So we just need to specify initial population size, done, number of time steps to project over, here let's say 11, and we use this function pop.projection, specifying the transition matrix, the initial population size, and the number of iterations, so time step to project over. Ta-da! And we can plot the results of the projection. We have population size in each age class or stage of the matrix and how it changes with time. So here in blue is the number of swallows age 1, and in purple age 2 in the population. So what you see here is that we have a first phase in which the population is not stabilized and the number of individuals in each age class can change, followed by a second regime or phase in which there is a stabilization. We see that the growth rate is constant in time and the proportion of individuals in each age class remain constant through time. So we call this first phase the transition phase. And the second phase is the stationary or stationary phase or regime. In the transient dynamics, first phase, it depends on the initial population. It's the time for the population to reach the equilibrium. And the damping ratio measures how fast the population will converge towards the equilibrium, depending on the initial population size. Once the population reach the stationary phase, the population growth rate is constant. We call it the stable or asymptotic population growth rate, which corresponds to, and we denote it lambda. as before. And the proportion of individuals in each age class is constant. And we call it the stable age structure or stage structure of the population. And these two quantities are independent of the initial conditions. They only depend on the transition matrix. So they're a characteristic of a different population. So if we look at the results of the pop projection function, we have different elements. The first one is lambda and corresponds to the population growth rate in the stationary phase. So here the swallow population in average is growing. So that's the asymptotic growth rate. The second element is the stable stage, which gives us the stable age structure in the population once we reach the equilibrium. So 44% of A1 and 55% of A2 adults in the population if it's at its demographic equilibrium. So that's useful if you observe values on the fields that are very different from these values. You know that the population has been probably perturbed recently so that it does not have time to return to its equilibrium, or that the values of demographic parameters you're using in your model are quite far from reality, maybe because they're environmental variation, for example. The third element contains the number of individuals in each age class, so 1 and 2 here at each time step, and the total population size at each time step in the last element of the results. And oh, sorry, that was not the last one, that was pop sizes. And the last one is the growth rate calculated at each time step. So we see first the population is decreasing and then is growing. And the more we go forward in time, the more the value gets closer to the asymptotic population growth rate. So we can directly calculate these quantities if we know the transition matrix, because they do not depend on initial condition. So that was the interesting numerical features of matrices I was talking about before. Just knowing the transition matrix, you can know the asymptotic population growth rate, because I'm not going to go into the mathematical details, but it corresponds to the dominant eigenvalue of the matrix. So in PopBio, there is this function called lambda, which gives you straight away from the transition matrix the stable population growth rate. So it's very cool. You don't even have to project the population to get this quantity. Same for the stable age distribution, which corresponds to the right eigenvalue of the matrix, whatever. We just use the function stable stage and we get proportion of juvenile and adults in the population at equilibrium. Same for the reproductive value at equilibrium, which corresponds to the left eigenvector. And it's saying that it's giving us the contribution of the different age classes of stages to the next, to the population in the next time step. So it's a relative value. So you always have the first age class, which has a value of 1. And here it's saying that adults contribute 1.5 times more than juveniles in producing the number of individuals in the next generation. Okay, so they have a higher reproductive values. We can also calculate the generation time with this function, which is giving the average duration, the average time between generations, and also correspond to the average age of mothers at birth of their daughters. So 4 years, 0.15 for the swallows. So they live, they are not so short-lived, supposedly. And then we can stop here, have a break for 15 minutes. Oh no, sorry, until 2. And then we'll come back and see how we can run some sensitivity analysis to determine which parameters are most important for the population dynamics. Okay, so see you after lunch or whatever time it's for you. See you in 2 hours and 15 minutes. Okay, so it's 2 here. We're gonna start again. C'est bon? No? Okay. So you should be able to hear me and see me. So I'm gonna share my screen again. And let's get back to it. So just before we saw how to write down the Lacey matrix and then use this Lacey matrix to project the population and calculate some interesting biological quantities. And now we're going to see what's the effect to perturb some of the model parameters on the population dynamics. So that's very interesting if we want to identify which parameters are the more important for population dynamics. So imagine female adult survival is reduced by 50%. Okay, let's say there is a disease or a predator hitting just on the adults that would reduce adult survival rate by 50%. So we can simulate this in the Leslie matrix. So we create a new Leslie matrix that we call the A swallow modified here, for example. And in this matrix, we divide adult survival by 2. Okay. So this is the modified Leslie matrix. And now let's project the population using this modified transition matrix. So we need an initial population size. We can consider here's 100 juvenile and 100 adults. We can project the population over 10 years using the pop projection function from the PopBio package. Okay, let's do it. This is what the results look like. So this is population size for each year of the projection. And what we can see here is that when we decrease adult survival, the population is now declining and it crashes over the first year of the simulations. Okay. Well, not so surprising. Adult survival is important for population dynamics. Okay. Now, what happens if we calculate the asymptotic growth rate of the population using this modified matrix? Well, lambda equals 0.86, so it's less than 1. The population is declining. Okay. So you can see why it can be interesting to change the value of a certain parameters and see what the impact is on the population dynamics. So here we might want to know then what happens if we modify juvenile survival or fecundity or chick survival. And if we do this for every vital rate in the life cycle, we are asking actually which demographic parameter contributes the most to population dynamics. Which parameter is the more important? Which one drives the population dynamics? Okay, so that's called running a sensitivity analysis. And it's very interesting because it helps us to identify which is the most important parameter. Okay, so when you want to run sensitivity analysis, it means that you're going to measure the impact of changing a specific vital rate or demographic parameter, measure the impact it has on the population dynamics. So to do this, you can calculate sensitivity, which measure the impact of a small absolute change, let's say adding or subtracting 0.001 to each demographic parameter, and looking at how population growth rate will change. Okay, so this is the mathematical way of writing it. What's the delta, so the change in lambda, when you change each demographic parameter, theta, by a small value. Okay, you can also measure the elasticity values, which is almost the same thing. It's just a bit different in that you are measuring the impact of a proportional change in each demographic parameter. So instead of adding or subtracting a value to each demographic parameter, you're just increasing it or decreasing it by a certain percentage. Okay, so what's the change in lambda of changing a specific demographic parameter theta by a certain percentage? So a change in theta in a proportional change in theta compared to the other parameters. Okay, so that's why we can write it this way, divided by lambda, because it's a proportion. Okay, proportional change in lambda. So both sensitivity and elasticity values are useful, but if you are interested in comparing the impact of changing survival value or fecundity value, because they're not on the same scale, it's more interesting to use elasticity because it's a proportional change. So it allows you to compare what's the impact of modifying survival versus fecundity or fertility. Okay, let's do it. It will help us to understand what we're doing exactly. Okay, so in R, you can do this using the vital sense function. But first, you need to list the different demographic rates in a single list. Okay, so here we call this list swallow parameters, swallow param. And in this list, I write down all the demographic rates involved in the life cycle. So chick survival, juvenile survival, adult survival, juvenile fecundity, and adult fecundity. Okay. Then I need to specify the equation of the Leslie matrix. So I use the function expression because I'm writing down a mathematical expression. And I list here the formula corresponding to each cell of the Leslie matrix. So if you remember what we saw this morning, the first cell was S0 times F1. The second one was S0 times F2 for the entry of new individuals in the population. And the second row of the matrix was S1 for juvenile survival and S2 for adult survival. Okay, so that corresponds to the Leslie matrix for the swallow that you wrote based on the life cycle. So now that I have the list of parameters and the equation of the Leslie matrix, I can calculate the sensitivity and elastic values using the function vital sense. Okay, what it's actually doing, it's changing the value of each demographic parameter by a little amount and running the projection, calculate lambda, so that it calculates the elasticity and sensitivity values to so changes in lambda in response to a proportional or absolute change to each one of the demographic rates. So if we look at these results for the swallow, we have a list for each demographic parameter. In the first column, we have its value, and then the sensitivity and elasticity values. So if we look at sensitivity, we see that it's higher for chick survival and adult survival. If we look at elasticity values, we see that it's higher for adult survival. Okay, so if we can it's better to look at a graph. Okay, so that's just a plot of the sensitivity and elasticity values. It's easier, especially if you have many demographic rates. So if we want to compare the survival, the importance of the survival parameters between them, we see that chick survival, that sensitivity is higher for chick survival and then for adult survival. And then if we look at elasticity values in purple, we see that actually survival rates, so elasticity for survival rates, especially for adult survival, is higher than elasticity values for fecundity parameters. So what these results are showing us is that the key parameters that govern the population dynamics for the barn swallows are survival rates, especially adult survival rates, for which the elasticity value was the higher. And it means that the best strategy here, if we want to increase the population size of barn swallows, the most efficient strategy would be to try and reduce adult mortality and chick mortality, which was the second most important parameter. But an action that would be focused on fecundity, for example, nest protection, would have less impact on the population dynamics, because we saw that sensitivity and elasticity values were lower for the fecundity parameters. So in the case of the barn swallow, it's really like survival and adult survival specifically that are the most important for population dynamics. Okay, so we can try and run it in R. So you have the script on the website. It's live demo 2 for class 3. We can load the PopBio package to project the population and the ggplot2 to make the graph. I forgot to write that in the previous live demo. We start by listing the demographic rates, S0, S1, S2, F1, F2. So you can see in the RStudio window here the object you just created. Then, based on these demographic rates, we create the transition matrix. It has 2 rows. Okay, I list the values and we can have a look at it to make sure it's correct. 0.3, 0.6, 0.5, 0.65. Okay. Then we can directly project the population using the matrix. We just need to set an initial population. Let's say 50 and 30. It's just random here because I'm not basing this on any real study case. So I could have picked another number. It doesn't really matter. Let's say we want to project over 11 years. Or we can increase this number a bit just for fun. Let's say 20 years, okay. And project the population using the pop projection function. I give the transition matrix, initial population size, and number of time steps to project over. Hop, it's done. It's really instantaneous. Let's have a look at the results. We have the number of individuals in each age class over the 90 years of projection, because we projected over 20 years. That's the first year. So the last one is going to be 19. Okay, we have T-1 estimates. We can look at the total population size going from 80 to 187 here. So the population is growing. It's always better to look at a graph. So let's make the graph here. Okay, we can see the first transition phase at the beginning, and then it quickly stabilizes with a constant growth rate and a stable proportion of individuals in the 2 classes, age classes. If we want to know exactly, I didn't write that in the script, but you can actually, there's a function called damping ratio, and it's telling you when the population will reach the equilibrium. So here it's after 10 years, attack. So here it will have reached the equilibrium. So we see that at the beginning there are big changes in growth rate, and here we just don't see it if we just look at the curve, but maybe on the log rate it's getting closer and closer to the equilibrium, and here it has perfectly reached the equilibrium. Then we can calculate the lambda asymptotic population growth rate, 1.05, the stable stage distribution, 44% of juvenile, 55% of adults, the reproductive values, generation time, and run the sensitivity analysis. So I list the parameters, the equation, and then based on these two objects, I can run the sensitivity analysis and look at the results. Okay, let's plot it. And here you get the same plot than in the slides with the sensitivity and elasticity values for each demographic rate of the life cycle. And as I said before, what the main message here is that fecundity parameters do not seem to matter. Yes, they matter less than survival rates to drive the population dynamics. Okay, so that's it for this example. Let's go back to the slides now. And let's go back to what we just saw that is called deterministic matrix population models, because we did not include any variation in demographic rates in the model. So we considered that survival fertility parameters did not change in the simulations with time or among individuals of different age class. Okay, so these types of models, the deterministic matrix population models, they are also based on other assumptions. We talked about it briefly before. We are just modeling here the female part of the population. So this type of model that we call one-sex model, they're suited to species that have a balanced sex ratio, but in which males are not limiting for the reproduction. But imagine if you were working on deers or other species which have a skewed reproductive success, with some males monopolizing most of the females, or species with a biased sex ratio, then you would probably need to use a two-sex model, modeling the males and the females in the population that would both drive the population dynamics. Okay, so it's possible, but we did not include it in the simple version. As we said, also, this type of model is suited for species that have a one breeding season, that all individuals breed at the same time. It's a birth pulse population, because we are using discrete time with reproduction happening and then what happens during until the next year, etc. Okay, so this wouldn't work very well, for example, if we were working on humans, because they can produce offspring any time of the year. Okay, so in this case, we would use another type of model, like a continuous time birth flow, a model in which individuals could breed at any time. Okay, and also we considered an exponential growth or a decay in the case of a declining population, but we did not include directly density dependence. It's also possible to do it, but a bit more complicated. And as I just said, the most important hypothesis here, not the most important, but an important one, is that we considered constant demographic rates. So no environmental stochasticity and no demographic stochasticity. So probably this type of model is better for species that live in stable environments in which we do not expect too much variation in demographic rates. For example, in protected areas. And in the case where we expect the no density dependence, like a species that would be recolonizing its habitat or recovering from overexploitation, for example, you do not expect density dependent mechanisms to be too important there, okay? Or a species that dispose of unlimited resources. In any case, even if for some reasons you decide to use these simple models for cases that do not exactly match these assumptions, like for example, if you expect that there is some variability among years, but in general is relatively stable, you know that the population size that you're projecting might not reflect exactly what's going to happen in the future. And of course, it's very hard to be sure that the demographic parameters will not change in the future. But even if the projections are not exact, it's still very interesting to run this type of deterministic model for the sensitivity analysis part, because it's a sensitivity analysis are a really useful tool to identify the key parameters for population management. Okay, so even if they're really simple, these types of model remain interesting for the sensitivity analysis. Okay, but if you want to go for a bit more complicated models, okay, you like R very much and you're not scared of stochasticity, you can do it. And now we're gonna talk a bit about these types of model for cases in which you think it's very important to include variability in the environmental conditions. Okay, so now let's move on to stochastic models. So of course we know that environmental conditions are rarely constant, and they are most of the time unpredictable fluctuations in the environment and therefore in demographic parameters of the species we are interested in. Okay, so demographic rates can vary over the years. And as a consequence, there are stochastic fluctuations in survival, reproduction, and population size over the years. This can reduce the long-run population growth rate and increase extinction risks, as we saw for the count-based PVA, especially in cases where you have several bad years in a row. It can really drive the small population to extinction. Okay, so it's especially important for environmental variation can have consequences on the population dynamics. Okay, so stochastic matrix population models. The idea that is behind these types of model is that instead of using a single transition matrix to project the population, we're going to be using a series of transition matrices. So imagine that we create one transition matrix every year. We pile up all the transition matrices and we project the population using these different population transition matrices. Okay, so that's the idea behind the environment, how to include environmental stochasticity in the model. So let's take an example. The crested newt example, in which it's been observed that there is some interannual variation in demographic parameters. So adult survival is 0.52 in average, but in 8 years of monitoring, they found some years it was 22%, and some other years it was 75% of the adults surviving. Okay, same for fecundity. In average, females produced 3.07 juveniles, but it could vary from 0.3 to 5.4 in over a 10 years period. Okay, so there is some important variability in the demographic parameters. And in this study, they identified some environmental factors that were responsible for variability in demographic rates. And the bad years were years in which there was a dryness in the pond in spring, which happened about 1 year every 3 years. And in cases where the pond was completely dry in spring, this would induce a quasi-complete failure of the reproduction certain years. Okay, so how can we take this type of information into account and use it in the projections? Well, first, this is the life cycle graph of the crested newt. So it's a pre-breeding transition matrix. We have the age 1 immatures, the age 2 subadults, and the age 3 and more, the adults. Okay. The immature can survive and become subadults. The immatures do not reproduce, but the subadults do, with a probability alpha 2 times f times f0. Alpha 2 represent here the proportion of subadults that can breed. Okay, it's not all of them. In this case, I think alpha 2 is 80% of the subadults that can reproduce, if I remember well. Then the subadults can survive and become adults with probability S2. And the adults reproduce with probability alpha 3 times f times S0, which is the survival of the newborn. And I think, if I remember well, alpha 3 is actually 100% of the adults reproduce. And they can survive and remain in the adult age class. So this is what the Leslie matrix looks like. You have the diagonal here with survival rates, and here the production of new individuals via breeding probability, fecundity parameters, and survival of the newborn, first year survival. Okay, so there are different ways we could include stochasticity, environmental stochasticity in the model, or annual variability in the model. You're going to see two different options here. The first one is using the mean values with some variability around this mean annual. So some years survival is going to be a bit better, and survival and fertility, and other years is going to be a bit worse. Okay, so that's adapted in cases where you know that the environment is relatively constant with some random variation around the mean values. So let's start from the deterministic matrix. I just showed you the equation. So if we just replace the parameters with their value that have been estimated, in particular using capture-recapture methods, we end up with this transition matrix with the immature, subadults, and adults. Okay. Then we want to draw some little variation from year to year in between on each one of these demographic rates. So we will simulate values from a normal distribution. Mean for the first one, for example, immature survival, the mean is going to be the average survival with a certain standard deviation estimated from the field data that we know that survival can vary from 1 year to the next. So here for this example, I just use 0.15 for every demographic rate for survival and 0.5 for fecundity, but you can actually estimate these values from your data. if you have many years of monitoring, and you have the annual mean survival, and if you estimate the variance, you can get to the standard deviation. So instead of having just one value for each demographic parameter, I now have a distribution for immature survival, subadult survival, and the different fecundity parameters. And I can draw randomly from this distribution to construct a different transition matrix every year, okay? And use these values in my simulations. So let's pile up the stochastic transition matrices. We create an empty object, an empty list, in which we will store instead of having just one transition matrix, we're going to have a different one every year, okay? So we loop over the number of years, for example, we want to project over, okay? Each component of the list is going to be stored in this object that we created just before. And instead of having just one transition matrix, now I'm going to sample from the distribution for alpha 2, sample from the one value from the distribution of the fecundity, and same for each demographic parameter. Okay, so that's survival. Okay, so it's the same equation for the transition matrix, but I draw a different value every year. And then it's the same principle that I need to define the number of years I want to project over, the initial population size, and the number of repetitions this time, because you cannot do just one projection because there is some random variation in your simulation. So you want to repeat it a large number of times, so 500 or 1,000 times, to be able to have the amount of variability in the population trajectories and calculate a mean trajectory with some confidence interval around. So you use the stoch.projection function to do this from the package popbio, like before, okay? So you enter the pile of transition matrices, initial population size, number of time steps to project over, number of repetitions, and here you can see the results is printed here. Each age class in column and in rows you have the number of different runs, the number of repetitions that you've run in your model, okay? So we can plot the distribution of population size after 20 years, and I don't know why I wrote a question mark here, suspense. So this is the population size at the end of the simulation. So we have some populations that have gone extinct with 0 individual left. Most population have a small number of individuals, around less than 100, I guess, and few populations have been growing very, very much. Okay, some have more than 30,000 individuals. Okay, so the probability to have this one is very low. Okay, most of the populations of population trajectories are around here. We can calculate the long run stochastic growth rate because now we just we don't really reach an equilibrium because there is some stochastic variations. So we calculate the long run stochastic growth rate. We don't call it asymptotic because there is some variability, okay? So you can use the stoch growth rate function, giving it the sequence of transition matrices, the number of time steps that you want to use to calculate the stochastic growth rate. And this is just to print different details in the results, okay? And if you, using this function, you'll see that it's giving you different results. So the first one is the long-run stochastic growth rate calculated using Tulja-Purkar approximation. So it's like the guy who wrote the equation to calculate it. Or the second value is using the simulation to calculate the stochastic growth rate. So if you want to, so using this value is the best way, probably. If you use this value, you have to make sure that the number of iterations you run the projection over is big enough to make sure that you've reached the enough iterations to calculate the stochastic growth rate. Okay, it's like t have to be as close as possible to the infinity if you want to get close to the approximation. Okay, so these two values should be close together, except if you don't have enough time steps in your simulations. And it's also giving you a confidence interval around the value for lambda. And you see that it's called lambda, but it's on the log scale. Okay, so remember that if you want to get back to the population growth rate, you have to exponentiate this value. So here we get population growth rate, asymptotic long-run population growth rate, 1.037. So in average, the population is growing, but there still is a risk that the population would go extinct. And we can calculate this probability of extinction. So we can use for that the stoch.kasi.x function. We enter the list of matrices, the initial population size, the extinction, quasi-extinction threshold, which is the same principle that what we talked about before, the minimal number of individuals that have to be left in the population for it to be viable. So you decide this threshold, number of repetitions, time steps to project over, and we repeat this calculation over a certain number of repetitions to get a robust estimate of the distribution of the probability of extinction. Okay, we just can see that on this graph here. We repeated for 10 times the calculation of the extinction probability. So you see that for the crusty newt, over the 50 years of simulation, probability of extinction of the population going extinct is below, it goes up to 1%. So it's very low, we can say, okay? If we want to calculate the mean probability of extinction in 20 years, we just calculate the mean over the 10 repetitions and take the 20th value of this vector, because we are interested in the probability of extinction in 20 years. So that would be less than 1% for the newts. Okay, so now imagine that instead of including some random variability around the mean values, you could also choose to model catastrophic events like the dryness of the pond in spring, which induced the reproduction failure. You might want to model directly these catastrophic events and to see what is the impact on the population. And you can also vary the frequency of these events and see how varying their frequency will affect the population dynamics. So that's a different way to introduce environmental stochasticity. So now we define, in our case, we know that it's fecundity that is mostly affected by the dryness of the pond. So in normal years, fecundity is about 3 female produced by a female. In bad years, so years in which the catastrophic event happened, fecundity would go down to 0. Okay, so it's an extreme situation, but you would take these values from your system. It could be, it doesn't have to be 0. It could be just a reduction in some parameters, and so on. So based on the normal versus bad years, we now define 2 different transition matrices, one for the normal years, in which we use good fecundity parameters to create the matrix, and it's still the same equation for the matrix, and another matrix in bad years, years with catastrophic events, in which fecundity is down to 0 in this example. Okay, and to project the population, we now gonna pick from in this one or the other matrix to project the population. So if we say that, we said before that on the field, we've observed that the bad years or the catastrophic events were about 1 year out of 3 in average. So you can set this frequency of catastrophic events to 1/3, which means you're gonna pick about, in average, 1 time out of 3, the good normal transition matrix versus the bad year transition matrix. Okay, so you use this frequency to determine the probability of choosing one or the other transition matrix to run the projection. Okay, so to do this, you use the same function than before, stoch.projection, and you give as an entry for the transition matrix the list containing the good and the bad year matrices, and then you enter the probability of choosing the good year matrix versus choosing the bad year matrix. So this probability corresponds to the probability of the catastrophic event. Okay, so that's probability of normal year, probability of catastrophic event happening. And then you, okay, so I just explained that. Then you enter the initial population, number of time steps to project over, number of replicates, repetitions. And that's it. You project the population. And then it's the same than before. You can calculate the long run stochastic growth rate and exponentiate it to have it on the biological state. So the scale, the population growth rate. So here we see it's 0.88. This time it's below 1. So in average now, the population is declining in the long run. Okay. So we want to look at the probability of extinction with a bit more interest than before, because it's probably bigger. So we use the same function to calculate the probability of extinction, stoch.gazi.ext, with the list of good and bad matrices, the probability to pick the good versus the bad years, initial population size, threshold for extinction, number of replicates, time steps, and we repeat this calculation 10 times to get the more reliability in the results. Wow, quite different than before. Huh? The probability of extinction reaches 100% after the 50 years in these simulations. Okay, so it goes from zeros at the beginning of the simulation, and after 10 years, it's already up to 60% in average. Okay, so you see that the impact of this catastrophic event on the population, it has more impact than when we just included a little variability around the mean values of the demographic parameters. Okay, so we can calculate the mean probability of extinction after 20 years, same way than before, and now we are up to 83%, so it's much bigger. So it's obviously it's interesting to evaluate the sensitivity of these results when we change the amount of environmental variance. So the standard deviation of the normal distribution, we use to create the distribution of the demographic parameters. In the case of catastrophic events, we want to change the frequency of the catastrophic events and see how it will affect the results. And you can also evaluate the sensitivity of your results to changes in the other model parameters, initial population size, the extinction threshold, and the time steps over which you project the population. So we're gonna keep going with the live demo, because then we're almost done, actually. So I've been very fast. Okay, so let's go for the live demo on the Crested Newts. Hop. So I'm just gonna clean that. Okay. So we load the Popio package. We define the demographic rate for the newborn, immature survival, subadult, adult. 80% of subadults can breed. All adults breed, and fecundity is the same for adults and subadults. We can run the deterministic model. So we write down the matrix based on the life cycle. And we could run the deterministic simulation here using the swallow code that I showed you in the previous section. But here we can go directly to the stochastic simulations. So this function here will draw 5,000 values from a normal distribution with mean S0 and standard deviation of 0.15. Hop, I'll do this for every demographic rates. And here I just make sure that I do not simulate values of survival bigger than 1 or lower than 0. So I filter in the simulated values, and then we can plot them and look. Okay, so usually you would have these distributions from your field data, okay? On the field, you collect data, and using capture-recapture analysis, you would estimate these distributions. For the purpose of this example, I just simulated the distribution. Using these distributions, I create a list of stochastic transition matrices. So instead of having just one transition matrix, I have a different one every year. So here I simulated 1,000 of them. Okay, so you see, if you look at them, they're very close, but a bit different every year. So here it's 0.38 and here 0.37. Here 0.71, 0.27, the difference is bigger. And they will be very different depending on the amount of the variance in the demographic rates that you estimated from the field. These matrices will be more or less different among them. Okay, if there is high interannual variability, some years demographic rates will be high and other years they will be much lower. Let's run the projection for 30 years. Project the population with the stoch.projection function and look at the results. So I have 1,000 rows here because I have 1,000 repetitions. And what we have here is the population size at the last time step of the projection for each age class. Okay, so if we want to sum up the 3 columns to get total population size and plot that, so that's the population size at the last time step. So you see many populations over the 1,000 are yeah, we had many extinctions and many populations with not so many individuals in them. Let's calculate the long-run stochastic growth rate. So here we have on the log scale, if we use Tulja's approximation, 0.032. If we use the simulation, it's 0.031, so very close because I use 50,000 iterations. So I try to get closer to the asymptote, the quasi-equilibrium. And we have the confidence interval over the population growth rate. If we exponentiate it, it's giving us 1.03. So in average, the population is growing, but the variability is much higher than before. So that's we can calculate the extinction probability and plot it. Oh, it's very low, of course. It's the first case where we had it less than 1% after 50 years. Okay. So that's why the population is growing in average. Yes, it's less than 1% after 20 years. Okay, so that was for the first way of introducing environmental stochasticity. Now, let's consider catastrophic events with good years and bad years with no offspring produced, which have a much higher impact on the population dynamics. So we write down the good year matrix, transition matrix, and the bad year transition matrix using zero fecundity. And we create a list with the good and the bad matrix. And it looks like this in the transition R point node point kata. We have the good and the bad transition matrices. Okay, so here we say that 1 year out of 3 is a bad year. I could, let's say that with climate change, it's going to get worse. Let's see what will be the impact on the population. So now I say, oh, sorry, it's going to be 1 year out of 2. That's very, very bad. Let's see how it will impact the population. So we run the projection with the function stoch.projection, give it the good and bad transition matrices, probability of bad year, initial population, number of time steps, and number of replicates. Let's have a look at the results. You see it goes very fast. That's population size for the 3 age class. And here, I guess everything will crash most of the time. Lambda is much lower than 1, 0.79. So the population is declining in average. Now we calculate the probability of extinction. And have a look at it. You see, I considered very bad environmental conditions with 1 year out of 2 that would be a bad year, and you see that very quickly the probability of extinction reaches 100%. So after 20 years, high chances that the population will be extinct, and it goes up very fast. Okay, and that's because I increased the frequency of bad years compared to the slides. So in 20 years, the mean probability of extinction is 99%. So yeah, poor newt in this case. It's very bad chances of the population to persist. Okay, so to finish, these models have, of course, assumptions and limitations. I'm just listing some of them here. As we said before, it's a one-sex model, so it would not be the best. It would not work very well for species with biased sex ratio or skewed reproductive success. For these cases, you'd need the two-sex model. it's a discrete time model without density dependence. We did not look into how to introduce demographic stochasticity in the models. You can do it with a little bit more of our code. It's easily doable. And it's important, especially if you work with small populations, because demographic stochasticity increasing the risk of extinction, especially for small populations. As the population is bigger, we can almost ignore demographic stochasticity. It becomes less important. Okay, and in the two options that we saw now, we considered that there was no trend or change in the mean of environmental variance. So mean demographic rates do not change in average, but you could also imagine if you identified a link between a covariate, an environmental covariate, and a demographic rate, you could also use a scenario, for example, for temperature, and include the relationship between survival and temperature in the model and use that to project the population. Okay, that's another way to do things, but there are many ways depending on your case, your study case. So we should always keep critical eyes on the results, of course, because the essence of projection models is that we are trying to make projections in the future. So we are making strong assumptions about demographic rates and environmental conditions in the future. So there's been several papers in the literature that have been evaluating the use of PVAs in conservation. And some studies have shown, like on 100 and something species, that it worked really well, that the predictions of PVAs actually match quite well what was observed on the field afterwards. But this is a case when you have strong data to estimate reliable demographic parameters. So for some other study cases, it doesn't work so well, especially if there is a trend in the environment, or for small populations, you need to include demographic stochasticity, etc. So it's very important to have good data to parameterize the model and good knowledge of the biological system. So, for example, short-term studies are often associated with an underestimation of the variance of demographic rates, because you have few points in the data to estimate the variance, so that you can underestimate the extinction risks. Okay, so it's things that we need to keep in mind when we run PVAs. And it's always good to make predictions and then go back to the field, collect more data, and compare the predictions with the new data. Anyway, these types of models remain useful when you have good knowledge of the species biology, the life cycle, and good estimates of demographic parameters. And as we said before, even if the number of individuals does not match exactly what your predictions are, it's still very useful to perform sensitivity analysis to identify which demographic parameters are key to drive the population dynamics. Okay, and the rest I've said before. In these models, matrix models, survival and fertility rates are structured by age or stage, but for some species, it's not the case. It's better structured by body size, for example. So in these cases, you would rather use other types of models, like integral projection models, for example. And there are many more complicated models matching specific study cases. So as we mentioned before, if you work on small populations, you might want to consider to include the impact of demographic stochasticity. There are density-dependent matrix population models, two-sex models if you have skewed reproductive success. This I talked about. Continuous time models if it's a birth flow species, and you might want to include even interactions between species or, okay, so that's just a few other options that are there. And just to cite a few references, these are there are many papers on PVA. Morris and Williams' Practical Handbook for Population Viability is very good for beginners. Matrix Population Models is a complete overview of many different types of models, the math that are behind. Paper from Brooks in 2000 has evaluated the efficiency of PVAs in different systems. Yes, and a few other papers, but many I couldn't cite here because we don't have enough space. Okay, that's it. I hope I was clear and you got some interesting things from this class. Okay, back to you, Olivier. For the final word.
Yeah. Okay. Okay, thank you, Sarah. So we have a few words of conclusions, and like it's 4 or 5 minutes, and then we'll be done. So let me find those slides, conclusions. Okay, and I'll remove that and that, yeah. Okay, so that was a workshop on quantitative methods for population dynamics. And population dynamics being defined as the variation over time of population size here. And we had a look to the mechanisms, demographic parameters, how to estimate population size, and also Sarah told you everything about matrix models and population projection models in general. So in details, we had a look to counting methods, the detection issues, and Aurélien showed you 3 types of model to estimate population size: capture-recapture models, distance sampling, and end-mixture models. I introduced you estimation of demographic parameters, and in particular survival probability and transition probabilities, including a dispersal. And Sarah covered population projection models with count-based PVAs and structured model with age and stage structures and sensitivity analysis, deterministic and stochastic models, which was great. And a few, some recommendations for you to analyze your data with models. And we called it the art of modeling, but well, we like to think it's an art, but so the first thing to do is, as usual, but that's something we sometimes forget when we are into the modeling, the analysis. We like to do our models and analysis, and it's always a good thing to remember that you should make your ecological question explicit and go back to it as often as possible. Then think of your model based on your question. You don't need to go for complex and fancy models all the time. Start simple. That's a general advice. Start with a simple model, like with a simple life cycle, constant parameters, and try to make sure that everything runs smoothly. And then from there, you can add complexity one step at a time, based on your understanding of the biology of your system and the data you have. But start simple. It's always something we forget, like thinking about the question and the model, but start simple and build from there. And it's also a good way to see where things are not working properly and where the bugs are and so on. So I guess it's time to say till next time. But before we leave, just a few information. The website will be updated with the video recordings. So it's already on YouTube. I'll post the link on the website, and we'll do some editing of the video. For now, you can have a look to the videos, but it's a kind of there are many breaks, and so it's a bit boring. But we'll do the editing soon, and you'll get the video recordings cleaned up. And also we'll update the website with your feedbacks. So we kept a track of the chat and the questions you ask on the chat. And the idea would be to have a section on the website with a kind of the frequently asked questions, you know, a specific tab that we would add so that you can go back to your questions and the answers we try to give. Kudos to the helpers, Colin, Thierry, Thibaut, and Valentin, who were much helpful and who gave very neat answers to your questions. Please, 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 can you fill in the feedback form that we made available through that link? This would help us very much to improve the material that we provided, and also to improve the way we deliver the courses for next time. Okay, so please fill in this link. It's just one page with a few questions, and that would help us very much. We're happy to provide a certificate of attendance on request, so you just send me an email if you need one. And the book is on its way, hopefully for next year, and we'll tell you more about it through social networks, or you'll hear about it hopefully next year. And I think that's all. So we're going to say bye, but I just wanted to have the whole team with me. Can you, Colin, Thierry, Sarah, can you come back? And we have also Aurélien. So we are with Thierry, I'm Olivier, Colin, and Sarah, and Aurélien is on Zoom. Aurélien, can you turn on your webcam, and Valentin as well? Hein?
Non, je peux pas allumer ma caméra.
Why?
I can't.
Hang on. And now, can you?
No. No problem. No.
I think you can now. Oh, Valentin is here. And Aurélien, now I think you have the right to open your... Yeah.
Ah, yes, it's working.
Yeah. So that's the whole team. The seven of us, 6 of us, 7. Why is Thibaut is not with us? So it was good to be with you. We hope that you enjoyed the workshop, and you'll find everything on the website. Do you want to say a few words, or just bye-bye? Bye-bye and enjoy. Bye.